We now move on to the description of the controllers of an excitation system. So far, we have been discussing the issues related to the modeling of the power apparatus, that is the exciter. Okay. But an exciter in some sense is incomplete without a kind of discussion of the excitation system is incomplete without the discussion of the controllers associated with the excitation system. In the previous class, we did the physical models of an excitation system. We did not actually derive in detail the model, but listed down the things which ought to be modeled. Okay. In today's class, in today's lecture, we discuss one of the major control systems associated with the excitation system, that is the automatic voltage regulator. Okay. So, in the previous class we studied two kinds of excitation systems, the static excitation system, whose basic model is a static one with limits, okay, which are determined by the generator terminal voltage. The control signal here is effectively obtained from the excitation system controllers. Okay. The brushless excitation system is a bit more complicated in the modeling aspects. The main issue here of course, is that the exciter alternator has to be modeled by a dynamic model, not a static model. And the diode rectifier, which is an uncontrolled rectifier, has got a limit, that is its voltage cannot go negative. Okay. The output voltage to the field cannot go negative. So, there is a limit associated with that. The control rectifier associated with the brushless excitation system is modeled in a similar way to a static excitation system. That is, it is a static model with limits. Okay. That is given on the left hand side. Of course, IEEE has come up with standard excitation models. In fact, the IEEE type AC1A model, which describes the model of a brushless excitation system, is given here. The functional block diagram of an excitation system, including not only the power apparatus, but also the regulators, limiters and stabilizers, which effectively form the control system. Remember, a control system is designed by us, it is more of a mathematical logic which is implemented using some physical elements. Okay. So, you can have analog or digital implementations of the mathematical logic, which really determines the behavior of the controller. Okay. Now, the mathematical logic in fact is a mixture of differential or dynamical equations, which have to be effectively numerically or implemented using analog blocks. Okay. Now, the most important or the core function of an excitation system controller is regulation of the generator terminal voltage. So, what it does is essentially keeps the terminal voltage of the synchronous generator, the main synchronous generator, almost constant. Okay. Now, so this is shown in a functional block diagram here, you can pay attention to that. There is a regulator. Regulator is something which tries to bring, in this case, the voltage near or equal to a set point value, it is called the reference value. Okay. But regulation is not the only function which is actually done by any excitation system controller. You also find that there are additional blocks corresponding to what is known as a power system stabilizer and limiters and protective circuits. So, you can have the overall functional block diagram contains something more than a regulator. Okay. Now, we will try to understand each of these blocks one by one. First of all is the regulation block. The regulation block essentially takes a reference or set point voltage. Okay. You compare it with the measured voltage, measured terminal voltage of the synchronous generator, and use this error signal, okay, to drive a controller, which in fact gives the control system which is used by the controlled rectifiers of the excitation power apparatus. Okay. So, this is a controller. So, this is a controller or regulator, you know. Now, this controller of course, is a mathematical function. It is some mathematical function like some things we will describe in a few moments from now. The voltage regulator effectively compares the set point which is given by us, okay, and the actual terminal voltage. Now, there is one point about the set point itself. The voltage reference of a synchronous generator terminals is typically going to be 1 per unit. Okay. We are going to really try to keep the generator terminal near about its rated value, but it is not sacrosanct that Vref should be equal to 1. You must have done in a course on any course on synchronous machines or electrical machines that by changing the excitation system voltage, remember the change in voltage reference here finally affects the control signal and eventually affects the voltage which is going to apply to the field of the main synchronous generator. So, by changing this reference voltage, say by increasing it, you are going to change effectively the field voltage and therefore, the reactive power output of the generator. Okay. So, if you recall a synchronous generator in its most simplest steady state model can be represented in this fashion. Okay. This is the synchronous machine terminals. If the machine does not have saliency, you can represent it by a synchronous reactance, which is nothing but equal to x d or x q, because they are equal. So, this is a steady state model of a synchronous machine. Okay. So, by changing EFD, if I change the field voltage, I effectively can change the reactive power output of the generator. Okay. Remember, the real power output of a generator can be changed only by changing the mechanical power or the mechanical torque of the machine. Okay. So, that is one thing you should keep in mind. So, if you look at the steady state model, okay, of a non-salient synchronous machine, by changing EFD you can change the reactive power output. Okay. So, of course, we do need to maintain the terminal voltage near about 1 per unit, but in case you change, if you try to keep this voltage slightly greater than this, remember that this, although I have represented the rest of the system as a voltage source, it actually is something like this. So, the correct way of representing the rest of the system could be, this is at an angle delta, the rest of the network. Okay. Now, the rest of the network again consists of transmission lines, etc. Simplified model of that could be inductances, etc. So, if I change the magnitude of the voltage, okay, the terminal voltage, effectively the reactive power output of the machine will change. Okay. So, Q of the machine can be changed by changing the reference value of the terminal voltage of a synchronous machine. Okay. So, of course, we will not want Vref to be very much different from 1 per unit. After all, the voltage in a synchronous machine has to be maintained at roughly what its rated value is. If you have a voltage which is much larger than that, you will have problems of insulation, okay, and more importantly, you may have overfluxing in the machine. Okay. So, one of the important issues here is what determines Vref? Well, one other thing is how much reactive power has the generator to supply. Okay. Of course, by reducing Vref, one can make the generator absorb reactive power. Okay. So, Vref is determined by how much the reactive power output of the generator should be. Okay. So, a plant operator, a power plant operator could tweak around this Vref near about the rated value of the synchronous machine. So, you of course, we can expect Vref to be say 1.02 or 1.03, okay, but please do not expect it to be 1.5 or so. That would really be much larger than the rated value, okay, and that would tax the insulation of the synchronous machine windings, and moreover the flux in the machine, the fluxes in the machine would become greater, the flux densities in the machine would exceed the saturation value in this case. Okay. So, remember the flux densities in the core are going to be dependent on the voltage of the machine divided by the frequency of the machine. Okay. So, in steady state B will be proportional to V by F. So, one of the reasons why you cannot make Vref too large, okay, is that you will go into saturation. If you go into saturation, the machine becomes non-linear. Okay. That is one of the, it will increase if the flux level increase, it will increase the heating in the machine as well. Okay. So, that is one of the major points which you should remember when setting Vref. Okay. Of course, Vref can be less, you can have Vref as 0.98 per unit, that is also feasible. Like, you may under low load conditions want the generator to absorb reactive power, in that case you would reduce Vref of the machine. Okay. So, this is basically what goes into deciding what Vref of the machine is. Okay. Now, once you have got Vref, you have decided what Vref should be, the power plant operator has some freedom in deciding that. It is compared with the terminal voltage of the machine. Okay. So, now the question which you would which needs to be asked, is this controller whichever is there, is it going to drive this error to 0, that is, will it make Vref exactly equal to V? The answer is, well, it depends on the mathematical function used in this controller. Okay. Now, another interesting variation which you see, is instead of maintaining V is equal to Vref, in some machines or in some situations, Vref is, you try to maintain Vref equal to V in most machines. Okay. So, this error is driven either to 0 or near 0, that is what your controller should do. It depends on the mathematical function you are using, but the aim of course would be to reduce the error almost to 0. Okay. That is Vref approximately equal to V. Okay. So, that is why it is called a regulator, a voltage regulator. But in some situations you would not necessarily try to keep Vref V almost equal to Vref, but you can have Vref almost equal to V minus K into the magnitude of current going out of the machine. So, you can have a situation like this as well. Okay. So, you can instead of having a control system like what I have shown you before, that is just having V, what you can have is this is known as a load compensator. Okay. So, the thing is that, of course, this usually is positive. The point is that instead of keeping V equal to Vref or almost equal to Vref, we will keep V plus K I is equal to Vref. Okay. So, in case I is large, okay, and depending on this value of K, if it is non-zero, you will find that Vref is not maintained at V is not maintained at Vref, but slightly lower than Vref. Now, the question is, why do this, add this additional complication here? The thing is that if you have got two machines which are connected to the same bus. So, this is two synchronous machines connected to the same bus, and both these machines have an excitation system. Okay. So, both these machines have an excitation system, both are trying to maintain the voltage of this bus a constant, okay, at Vref. Now, what will happen is that in case both these machines are trying to maintain the voltage here at Vref, the question arises is how much which each individual machine contribute to keeping this voltage at Vref. Now, normally what we do is we make this change to the automatic voltage regulator, so that if a machine contributes more current, or more load, okay, more current, In that case, this gets modified, this additional term essentially reduces V, makes Vref slightly less than V, rather makes V slightly less than Vref. The reason it is done is that you can then impose a sharing between these two generators. If one generator supplies more current, okay, automatically what is done is that this becomes larger. Okay. If this becomes larger, Vref will not be maintained, V will not be maintained at Vref, but slightly lower value. So, what will eventually happen is that this synchronous generator will start, if this I increases, effectively what will happen? It will try to reduce, this is the exciter power apparatus, this is the controller. If this one of the generators takes on more load, it tends to decrease, it will tend to decrease the final exciter voltage, and therefore, that what happens is that it prevents one generator from taking all the load. In fact, by choosing a case appropriately for both machines, okay, for both machines, if I choose my K appropriately, I can actually impose a proper sharing agreement between these two generators. So, no one machine pushes in more current than what is necessary. Okay. So, what happens is that you make the excitation system or the exciter field voltage a function of the load current. Okay. So, if you have got two alternators or three alternators which are bused together, they are connected to the same bus, and your automatic voltage regulator is trying to maintain the voltage of that bus at Vref. Okay. So, each generator has got an independent voltage regulator which is trying to maintain one common bus voltage at Vref. Then to impose the sharing of reactive power, one may have to put this additional component in the control system, which makes the excitation field voltage dependent on I. Okay. So, if one generator starts pushing more current, it automatically self corrects. So, that is the basic idea. So, the sharing of the generators can be imposed by choosing appropriate values of K for each generator. Is it okay? But of course, if the generators are not bused together, in fact, typically what happens is each generator is connected to its unit transformer. It is called a generator transformer, which steps up the voltage, and the generators are bused together at the high voltage side. So, this is the low voltage, say 15 kV, and this is 220 or 440 or 400 kilovolts, say. So, if you have got a situation like this, each generator maintains its own terminal voltage constant. Okay, it is not maintaining a common bus voltage at Vref. So, in this case, it is not necessary to have a load compensator, okay, for sharing of, because you are not maintaining a common bus voltage at Vref. Okay. So, but in case two generators are bused at a common point, okay, directly the terminals of the generator are connected to a common bus, and then you step it up, say, or use it for other purposes. In that case, you need to have a load compensator to ensure that while trying to meet a common objective, the sharing of the load is done as per our design, okay, this K value. Okay. So, I leave it as an exercise for you to show that indeed, if I choose K1 and K2 appropriately for say two identical generators, I can or two different generators for that matter, by choosing the K value appropriately, I can impose a sharing of reactive power between the two generators. So, this is something I request you to try to prove. Okay. So, the steps are, just to make things simpler, assume two identical generators, assume that they are supplying the same amount of real power, okay. They have got the same mechanical power input, say, that is the values are equal. Let us assume that the Vref for both the automatic voltage regulators independently. I mean, there are two independent automatic voltage regulators is the same, and these two machines are bused together at a common point. Okay. Then by choosing K1 and K2 appropriately, the reactive power sharing can be imposed as desired by us. Okay. So, you can choose K1, K2 as per your reactive power sharing requirement in this situation. Okay. So, this particular function of Vref being modified, this summing point being modified by applying an additional correction signal here, you can say, which is dependent on the loading of the machine, alters the characteristic of the machine, alters the voltage. You are not no longer maintaining V is equal to Vref, but maintaining V plus Ki approximately equal to Vref. Okay. So, this is called a load compensator. It is usually not used in situations where a common objective is not being met by two excitation systems. For example, in this case, when the machines are bused together at the high voltage side and your voltage regulator is trying to maintain these voltages constant, it is not necessary to apply this load compensator, and in such situations it may be absent. Okay. So, please chew upon this point. Now, if you look at the other functions which are shown in this block diagram, there are limiters and stabilizers, but we will come to that a bit later. In fact, I have already given you a hint where this limiter may come into play. For example, if I have given Vref 1.05, okay, and you also see that the frequency of rotation of the machine has come down, it is less than the normal, say 50 hertz, okay, the frequency has come down. In that case, the flux level in the core may be higher than what is sustainable by the core, in the sense this core will start heating up, okay. So, and will also get saturated. So, in such a situation, you may require to have some overriding functions which prevents, okay, the flux in the machine from becoming too large. So, what you have to do is, if effectively under such situations, if you see that the flux limit is being exceeded, what you would do is override what you want to have, rather override the regulator, in the sense that do not aim to achieve Vref is equal to say 1.05, but reduce this Vref to a point at which the flux is not exceeding its rated value. Okay. So, this kind of protective and limiting functions can be there. Basically, what they do is override Vref or at least change Vref. Okay. So, what you have usually is the stabilizing and limiting functions. So, what you have normally is Vref, and in case the generators are not bused together right at the terminals, this is the structure of the summing point of the voltage regulator, but Vref itself may be overridden, in the sense that some additional controls, if you, for example, if I put some additional input here, okay, say 0.05 per unit, I add at this point. So, what will happen is that if the controller here drives this to 0, what you will have is Vref is equal to V minus 0.05, or in other words, Vref minus V plus 0.05 is equal to 0. So, what in effect by doing this I have done is increased Vref. Okay. So, if you have any additional signals adding on to Vref, they in effect compromise on this voltage regulation function. V will no longer be equal to Vref. Okay. So, for example, if there is an overfluxing situation, you may adjust, this becomes minus, you may adjust this Vref by an additional signal which adds on to this summing point. So, I may add on minus 0.05, so I augment this summer, what comes out of this summer. So, finally, Vref, V will not be equal to Vref, but slightly less than Vref. Okay. So, this is what effectively limiting functions does. The other function which we have seen here is, so actually I will read all this. So, you have got Vref, this is the structure of a voltage regulator summing point, okay, without load compensation. So, we just have V here. This is what is normally required. You may have overriding additions or subtractions from limiters, and you may even seek to modulate, you may wish to modulate this voltage reference by some external stabilizers. Now, we shall discuss these stabilizers later in the course, but remember you can modulate these things. Now, one of the important things about limiters and stabilizers is, which you should be very clear about, is that limiters normally give 0 output if the machine has not hit any limit. Okay. Similarly, a stabilizer gives 0 output when the machine is in steady state. Okay. So, the overall regulation function of this voltage regulator eventually boils down to this and this. The summing point in this regulation function boils down to taking the difference between Vref and V, okay, in steady state if no limit is violated. So, the voltage regulator in some sense is completely enabled when no limiter or no limit violation has taken place. However, if any limit violation is taking place, some input will manifest at this point due to the limiting function, and V will no longer be equal to Vref, it will get overridden in some sense by this additional superimposed signal. During transients, the stabilizing function augments this Vref. Say you can be during transients, you could be sending in a modulation signal. How to derive this modulation signal is something we will discuss later. We may modulate this point. Okay. Why we need to do that? Do it? Well, by using this modulation function, we expect that we will try to improve the dynamic performance of the synchronous machine. Okay. So, this is what essentially is the things you will see at any summing point. One of the questions you may ask is, well, you have got this controller or regulator which takes this error, does some mathematical function on it and derives the control signal which goes to the power apparatus, the excitation power apparatus. The question is, can we not shift these limiting functions to this point? So, can we not, instead of changing the summing point here, can we have these overriding functions acting here? The answer is yes, you can. So, in some implementations of regulators, this limiting, the output of limiting functions and stabilizing functions are in fact added at the control signal level, the control signal which is sent to the excitation power apparatus, that is to the control rectifier of the power apparatus, okay, excitation power apparatus. So, you can have this kind of alternative structure where you are having the summing junction here for the limiting and the stabilizing function. Okay. Now, the main important point here is now what is the structure or mathematical function which are typically used in the controller block which is shown here, and also what are the mathematical functions which are used to implement these limiters and stabilizers. Okay. Now, to understand this, we will actually have to understand what are known as transfer function blocks. Well, you do not have to understand this in terms of what are known as transfer function blocks, but most of the excitation system, control system representations which are available in the literature come in the form of block diagrams. So, you should be able to write down the dynamical equations or the differential equations or the mathematical functions which really correspond to these block diagrams. Okay. So, mainly there are what are known as transfer function block diagrams. In fact, I have already shown you a transfer function block diagram. You recall this? This IEEE model of a brushless excitation system is in fact a transfer function block diagram. You see this S function here? Well, this S function is in fact the Laplace variable. Okay. We have used, of course, we have without actually explicitly defining these, we have already used these summation blocks. This is a product block. Okay. So, these are what are known as typical block diagrammatic components which are used in trying to model an excitation system. Of course, this block diagram here which uses Laplace variable s, in fact 1 upon s is what is known as is essentially an integrator, okay, an integration function. So, this 1 upon s here represents an integration function. Now, this of course, was a model of the power apparatus. Okay. So, what we did was roughly model the excitation alternator by a differential equation and then converted it into a block diagrammatic representation of this kind. We now move on to the block diagrammatic representation not of the power apparatus, but of the control system. Okay. Now, control system are something which we will be implementing. Okay. Now, what should be the structure of any control system? Now, it is usually made up of gain blocks, integration blocks, summation blocks and so on, and compactly written down in terms of input output relationships or what are known as transfer function relationships. Okay. So, let us just take a minor diversion. We need to build up this kind of expertise and try to understand some basic transfer functions, okay, which you will see. For example, consider the block 1 upon 1 plus st. Okay. This is a transfer function block. Okay. In fact, the simplest block one can have is of course a gain block. A gain block is a simply multiplies u by k to get y. Okay. A transfer function block on the other hand means something more. In fact, in a transfer function block inherently or implicitly there is some numerical or actual integration being done. Okay. So, this s in fact is a Laplace variable, 1 over s represents an integration function, okay, and s of course is a derivative function. So, what is 1 upon 1 plus st derived from? In fact, if you look at the dynamical equations, if you look at these dynamical equations, I have written them in fact, this dynamical dynamical model using differential equations is actually how this has to be interpreted. Okay. Why is why does this mean this? It is not very difficult to see. Suppose I do replace dx by dt here, okay, by its appropriate Laplace transform value. What you will get is, if I apply Laplace transform on both sides of the equation, you will have s into x s is equal to minus 1 upon t x of s plus 1 upon t u of s and y of s is equal to u of s. So, what you will have here is, you get this onto this side, you will have x of s into 1 plus st is equal to u of s, and as a result of it, of these equations, you will have y of s is equal to 1 upon 1 plus st into u of s. So, that is why this differential equation, after doing Laplace transformation of this differential equation, you get effectively this input output relationship. In fact, input output relationships have been discussed in the past. In fact, our when we talked about the modeling of a synchronous machine, when we actually correlated what we get from measurements, the frequency response obtained from measurements, we did use a transfer function representation of the synchronous machine. Therein also, the basic differential equation model of the synchronous machine was reduced to an input output relationship in by using this Laplace transform variable s. Okay. So, remember that 1 upon 1 plus st represents this transfer function. Of course, one should be a bit careful and precise. Well, there is no one to one mapping between this and this. in the sense that a different model of you can have a different state space or different differential equation model to get this input output relationship. For example, dx by dt is equal to minus 1 upon t x plus u, and then y is equal to 1 over t of u, okay, will also give you the same transfer function. Can we verify that? You will get s of x s is equal to minus 1 upon t x of s plus u of s, y of s is equal to 1 over t u of s. So, you will have so what you will get eventually is 1 plus s t of x of s is equal to t times u of s. So, y of s is equal to 1 upon t u of s. So, from these equations, okay, what we can get effectively is y of s is equal to 1 over 1 plus s t u of s. Is that okay? Y of s is equal to 1 plus s t upon t into u of s. Okay. So, we will have is equal to, I am sorry, so u of s by t is equal to y of s is equal to 1 of, we will just redo this. So, what you will have here is y of s, there was one small error which I did in our previous, this should have been x, this should have been x. So, please note this error. So, this should be x of s. Okay. In that case, of course, you will get this particular relationship. And just to recall what I was doing just now, I was just trying to show that this is an alternative representation of the same transfer function. So, what you will have is it should be x of s, this should be x of s, and as a result of this, okay, we will get so what I wish to say here is this is one possible representation of the transfer function, but this is another representation of transfer function. So, there is no unique way of representing transfer functions by state space. Okay. So, this is one example of that, but usually in this particular course I will just take this particular representation, it is very convenient, okay, of 1 upon 1 plus s t. In fact, I can split up this, if you look at this particular differential equation, okay, this is one possible representation of this transfer function. So, if you look at this differential equation, I can rewrite it as a kind of a integrator this is u and this is y. This is x, x is equal to y, okay. This is x dot, if you integrate x dot you get x, okay. X dot is equal to 1 upon t u minus x. So, this is what exactly this says, d x dot, that is dx by dt is equal to u minus x divided by t. Okay. So, this is what effectively is a block diagrammatic expansion, you can say, of this transfer function. Okay. So, if you see this, remember this. Okay. Now, see this what we have drawn so right now is actually quite interesting. The transfer function itself, that is what I mean. 1 upon 1 plus s t is an interesting transfer function. If you look at some simple things it does. Okay. If you have got u and y here, if I give a step change in u, what will y be? In fact, you can prove this by actually solving the state space equation and prove this, that if u is a step, then y is going to be something like this. This is y and this is u. Okay. So, the step change has some interesting features. You see that at the instant of the step, this transfer function has an output 0, it does not change. Suppose the initial conditions associated with this state x is 0, then if I give a step change in the transfer function, we will find that x remains 0 and as a result y also remains 0. So, there is no instantaneous change in y given a step change in u. So, y just remains where it is. Okay. But as time passes, you will find that y tends to become equal to u. So, the steady state gain of this transfer function is 1. Okay. That is y becomes equal to u. Okay. Now, of course, the same thing can be got, the same inference can be obtained directly by setting s is equal to 0 in this transfer function. So, a shortcut method of finding the steady state gain of any transfer function is to put s is equal to 0 in the transfer function. So, if you give a step input, the steady state value or the steady state gain for a step input can be obtained by simply putting s is equal to 0. Okay. So, you can say that this transient gain or the high frequency gain of this transfer function is actually 0, it does not instantaneously respond, but in steady state it takes on the value. Okay. Now, what is the nature of this curve? In fact, you will find that y is equal to u 1 minus e raised to t by capital T. So, if this step occurs at time t is equal to 0. Okay. So, this is a step change of magnitude 1 occurring at time t is equal to 0, the response is like this. The time constant t appears here in the response. Okay. So, it is a good idea whenever you come across any transfer function block, you should be able to correlate it with its time response under various test inputs. Okay. If you look at another interesting and important way of looking at transfer functions or interpreting how they behave is to look at the transient behavior. Okay. So, the transient behavior or the what you call the frequency response, we have actually seen the transient behavior for a step change. The frequency response of the transfer function can also be obtained, that is you vary the frequency and see the gain, that is u y upon u in steady state. So, what do I mean by a frequency response of any transfer function? You take this block, feed it by inputs of varying frequency. Okay. In steady state, if it is a transfer function, normally a transfer function in steady state would at the output, if it is actually a stable if it is a stable system, that is it is associated with a state space whose eigenvalues on the left hand side of the imaginary axis, then what you will see is that the output you will get also a sine wave, but its magnitude would have changed and it would have also got some phase shift. It could have got some it can have some phase shift. So, you take any transfer function, this is how you would measure the steady state frequency response. Okay. So, whenever people say frequency response, it is implicit that they are talking of the response under sinusoidal steady state conditions for input sinusoids, inputs u which are at different frequencies. So, what you do it, you do this experiment which I have shown you on the sheet here at a particular frequency, record the gain, that is how much is the amplitude with respect to the input amplitude. Okay. So, that is the gain, and also measure the phase shift. So, the phase shift of this, there will be some phase shift between this signal and that. So, you measure the phase shift. So, that is what will give you what is known as the frequency response. Remember, frequency response implicitly is the steady state frequency response of this system. Okay. So, you will get a gain which is a function of frequency, that is one important thing. So, the gain is a function of frequency, okay. The phase also is a function of frequency. It turns out for 1 upon 1 plus S t, the steady state gain is 1, okay. Steady state frequency, what you call the 0 frequency. When I say steady state, actually it means 0 frequency. The 0 frequency gain is 1, whereas the high frequency gain is low. How do I know this phase shift and the gain? Well, you can do it very simply using a transfer function. If I give you a transfer function, okay, if I want to know what is its gain and phase shift, all I need to do is put S is equal to G A omega, omega corresponding to that frequency which you are interested in, getting the frequency response, and you can get the answer. So, this is something of course you have done before, but we are just revising that. So, this is how it is represented. So, this is called a frequency response, okay, or rather the transfer function evaluated at this frequency. Okay. So, what is the magnitude gain? Well, that can be obtained simply by obtaining the magnitude of this complex number. Okay. So, that is what will give you the gain, and the phase shift is again obtained by looking at the argument of this complex number which results. Okay. So, what one thing you will notice is that this will always give a negative phase shift. This transfer function has a negative phase shift. In fact, at omega is equal to 0, the phase shift is 0. Phase shift is 0 degrees. At omega tending to a very large value, okay, a large value in this context means that omega t is much greater than 1. Okay. In such a case, you will find that omega t or t omega much greater than 1, you will find that the phase shift is minus 90 degrees of this transfer function. Okay. Similarly, at omega is equal to 0, the gain is 1, but the high frequency gain is 0, which correlates well with the step response. Just at the instant at which the step is given, you can say that the input signal in some sense is kind of changing very fast, or it has got a high rate of change, or it has got a very high frequency component. Okay. The transfer function does not respond very well, or has a very low gain to high frequencies. Okay. We will move on to one more transfer function, that is a kind of a important transfer function, just as the previous one was. This is S t upon 1 plus S t. This is an interesting transfer function again. You can verify that a steady state space representation of this is y is equal to u minus x. So, this is a change. So, this is a steady state representation of this system, or rather a state space representation of this system. Okay. So, if you look at this, can you guess what is going to be the response for a step change in input? Well, you can actually work it out, but it is not difficult to see that first thing is that the high frequency gain of this is going to be 1. If you look at the frequency response with omega large, the gain of this is going to be 1. For low frequencies, the gain is going to be equal to 0. So, in fact, we will not work it out, but a step change, for a step change, the response of this y is going to be like this. The final value is going to be 0, the initial value is going to be equal to whatever this value. Suppose this is 1, then this is also 1. So, this is known also as a washout transfer function. It is called a washout transfer function. The characteristic is that it has got a characteristic of a, in a sense, a high pass filter. It prevents slow changes from going through, but it allows fast changes to go through. Okay. So, its steady state gain is 0, its high frequency gain is 1, okay, and this is the state space representation. Now, from the state space representation one can easily get a block diagrammatic representation. So, it is quite simple. So, if you look at this, it is simply what it was before. The only thing is, this is an integrator. You can represent an integrator is in Laplace domain is represented by 1 upon s. Okay. So, this is u, this is y, and this is not y. Y in this case is this is subtracted u minus x, this is x, but there is an additional u, y is equal to u minus x. So, this is y, this is u, this is x dot, okay, and this is u minus x. So, this is known as a washout block. Remember, this extra thing here completely changes what you get. In fact, you can easily see that S t upon 1 plus S t is equal to 1 minus 1 upon 1 plus S t. So, it is not surprising you have got a block diagram of this kind, in which in fact, this is nothing but, this whole thing is nothing but 1 upon 1 plus S t. So, you got 1 minus 1 upon 1 plus S t. Okay. So, this is as far as one of another of the transfer functions goes. In the next class, we will look at a few more transfer functions, talk about what are known as what is a PI, a proportional integral regulator, and a proportional regulator. We look at, as I mentioned sometime back, the lead lag blocks. These are also special transfer functions, okay. And we will also look at the effect of limiters. Okay. There are two kinds of limiters. So far, I have implicitly assumed you know what a limiter is, okay. But you can actually have some variations of limiters themselves, and they eventually affect how the system response is going to be. Typically, a control system will be made out of either plain gain blocks in addition to summers, multipliers, and so on, and transfer functions. When I say transfer function blocks, the transfer function blocks themselves represent a linear system, okay, linear state space. Okay. Of course, if you put limiters in the transfer function, in that case limiters in transfer function blocks, the blocks which I have shown you, if I insert a limiter, it no longer is a linear system. But if you just remove that little bit complexity, transfer functions implicitly are obtained for linear systems or linearized systems, okay, nonlinear systems which are linearized around an equilibrium point. Okay. So, using these blocks or these mathematical functions or these you can say mathematical dynamical functions, we can actually try to design a control system which meets our objectives. Okay. So, I have just discussed some of the control systems which are used. Of course, rather the transfer functions block diagrams which are used, we can use these block diagrams selectively to get the dynamical as well as steady state response that we desire. Okay. So, that is what we will do in the next class.